Hello. The following video contains edited highlights of the 231st meeting of the American Astronomical Society. Due to the use of different recording equipment, video and sound quality will vary. Hello, this is Dr. Robert Mitchell of St. Ambrose University, and I'm coming to you from the 231st meeting of the American Astronomical Society. Astronomical Society meetings are semi-annual conventions where astronomers and astrophysicists gather from all across the country to present news, research, and recent projects in the astronomical field. This current meeting is taking place at the Gaylord Resort and Convention Center in National Harbor, Maryland, between January 8th and January 12th of 2018. Over the course of this video, I'll be bringing you edited highlights of the current AAS meeting, including some of the research and projects that are being presented here, as well as some of the exhibits on display. This is the main exhibit hall of the AAS meeting. Many of the research presentations at these meetings take the form of poster sessions, such as the session you're seeing right now. Attendees are welcome to wander around the main exhibit hall, examining the different posters and talking with the posters' presenters, asking questions and exchanging ideas. Posters are displayed on different days in the meeting and in different sections of the exhibit hall based on the particular subfield that the poster relates to. The ones you're seeing right now are mainly about efforts to detect and examine extrasolar planets. Those are planets in other star systems, a very popular topic these past several years, especially with the multitude of exoplanet discoveries made by such observatories and spacecraft as the Kepler spacecraft.
Hi, I'm Jackie Malengo. Gettysburg College. And this is almost 25 years of photometry from the National Undergraduate Research Observatory. I don't know if you want to name it down there. National Undergraduate Research Observatory. So many years of differential photometry of a very active spotted star, H21883, which is in the Pleiades, and we are looking for not only rotational period from the modulation from the spots, so you have star with big spots on one side, so longitudinally asymmetric, then as it rotates, the spots come in and out of view, brightness goes up and down. So we've been following the star not only for changes in the rotation period because the spots show up at different latitudes, but also for a cycle period, analogous to the sun's 11-year sunspot cycle. So far, we've found a cycle period of about 9 years, but they're really young stars that are very magnetically active in a saturated zone of magnetic activity. So they occupy a very interesting parameter space for active single cool dwarfs, and we're trying to see if we can take observables and connect those observables, like cycle period, differential rotation measure, to the underlying magnetic dynamo. Some observational constraint of what's happening that causes the activity.
Thank you. Here are some posters on research into gravitational waves, one of the newest and most exciting areas in the field of astronomy. Gravitational waves are literally ripples in the fabric of space-time itself, caused by the motions and collisions of very massive compact stellar objects like neutron stars and black holes. Astronomers have compared the introduction of gravitational wave observations to literally adding sound to movies. For the first time, we're actually able to hear the vibrations of the universe as well as see the light from optical light, radio, X-rays. Gravitational waves are literally a brand new way of observing the universe, completely independent of light and other forms of electromagnetic radiation. These posters are about supernovae, the explosions of massive stars and the remnants that they leave behind.
So I'm doing research on radio observations from supernova explosions, and what happens is before a star explodes, it's usually a red supergiant, and it blows off its outer layers in the wind. And so the wind's traveling out at like speeds of a few 5 and 10 kilometers a second, and it does this for thousands of years. And so when the star explodes, though, it becomes a supernova. There's a massive shock wave that blows through this wind, which gets ionized in the supernova explosion by big flash of ultraviolet radiation. And the shock wave is moving at 1,000 times faster than the wind. So as the shock wave interacts with the wind, it causes radiation to be emitted, which we can detect from radio telescopes. And by studying this, we can learn about, after the explosion, what the star was doing in the years before it died. So in 1 year of radio observations, we can actually learn about on the order of 1,000 years worth of pre-explosion mass loss history from this progenitor star. So we observed this one supernovae, which was type 2P supernovae, which are generally thought to be the smallest of the stars that explode and become supernovae. And they're generally thought to have fairly uniform and smooth winds. One thing we discovered with our radio observations is when we looked for it about 7 days after explosion, it hadn't turned on the radio, which meant that the wind wasn't very strong, or there wasn't much of a wind. But a few days later, we detected strong radio emission. What this tells us is we think, is that the mass loss history of the supernova was such that right before it exploded, it was starting to contract possibly, thereby losing less material. So we're seeing something that we didn't expect, a change in the evolution of this progenitor star, which might mean that this class of stars, which we thought we really understood, is not something we really understand as much at all, or at least not as well as we thought. So this is kind of a neat discovery. Hopefully it'll lead to more observations of similar supernovae.
Thank you. Thank you. That was Chris Stockdale of Marquette University in Milwaukee talking about his poster presentation for this AAS meeting. Here are some posters depicting educational and public outreach projects conducted during the total solar eclipse of August 21st, 2017. The first total eclipse to occur across the entire continent of the United States in 99 years, and as well as the first eclipse in the U.S. to occur during the era of social media. A marvelous opportunity for education among the general public. A recent addition to the AAS meetings are iPosters, electronic versions of the traditional poster sessions. So this is Ryan Plum of Pennsylvania State University presenting his poster at the AAS meeting.
My poster is about a galactic supernova remnant called W489b. Mainly, I found conflicting papers on whether or not it's type 1A or a core collapse. So what I did was, I looked through those papers and I found the main areas of data that we're using to decide what it really is. And that's being their metallic abundances like silicon, argon, within the remnant itself. What I ended up finding was that you can't base what the remnant is or how it exploded on those particular parameters. Abundances of the metals within the remnant are not all the same, and they vary pretty widely across the remnant. So what that really means is that you can fit both models of a core collapse and a type 1A at the same time, depending on how you weight your averages. So if I take mass weighted blobs or emission measure weighted blobs, we're not getting consistent results with both of those at the same time. So we need more lines of evidence, and we need to reconstruct the averages to figure out what it really would be. Everything comes down to what value you use. So if we use just an average mass or an average emission measure, you get two different models back. So we need more lines of evidence.
So it's still inconclusive as to what.
Yes, we're still inconclusive. The main idea I found was, I thought maybe there would be presence of a neutron star or a white dwarf within the area. Some people claim that there are candidates for a neutron star to be in there. Others are claiming that it's not possible. The white dwarf cooling time for this particular area is much older than it changed. So you can't really have a white dwarf in the area.
So it could be a neutron star.
It could be, if we can find one. It could be a black hole.
Now, if it was a type 1A, what kind of remnant?
Well, it's a dense cloud, so we would assume it to be spherical, but since it is in a dense area,
Still a lot of work to do there.
Yeah, still a lot of work to do.
AAS meetings also feature exhibits from industries and research consortiums, demonstrating the latest technologies, future and current space probes and telescopes.
Some exhibits are for online resources and databases to help astronomers with their research.
Publishing companies display the latest in books, textbooks, and periodicals. New designs of telescopes and other instruments. And even a gift shop.
In the afternoons, many of the attendees take a break in the sitting area on the main exhibit hall for socializing and networking.
After a full day of sessions and walking around the exhibits, it's nice to be able to sit down and rest for a while. Many of the attendees take this opportunity to catch up on their work, socialize, grab a quick nap before the next session. I've been to many of these meetings, and each one has something new to offer. Today, one of the exhibits has a mock-up of a balloon-based instrument, which they use to send instrument packages up as high as 10 or 20 miles into the atmosphere. High up enough to get above 99.9% of the Earth's atmosphere, which is almost the minimum height needed to do really good infrared observations of the universe.
Oral presentations are another very important part of AAS meetings, and are usually allocated to the biggest names and the biggest stories in the field. Here's an excerpt from a talk on the recent detection of gravitational waves from a collision of two neutron stars.
So just 1.7 seconds later, and this number is very important, the time lag between the merger and the detection of a burst of gamma rays by the Fermi satellite and the integral satellite. There was a burst of gamma rays that lasted for a couple of seconds and had two distinct components. A soft component that you see in the top panel, and then a harder component that has a sharper peak that you see in the middle panel and the third panel there. So now, I very deliberately am calling this a burst of gamma rays and not a gamma ray burst. And the distinction between this and this choice, I hope, will be more clear to you as we work through the physics that the neutron-star merger presented to us. The very discovery, the spectacular discovery of gamma rays by these two satellites were the first photons that were seen, first light that was seen from gravitational waves ever. And the very next thing we want to do is to try and pinpoint spatially exactly where this merger happened. Now, as fantastic as gravitational wave interferometers and gamma ray burst detectors are, they both have one weakness. They both have very poor spatial localization on site. So they can tell you very precisely when something happened, but not where it happened. And that's where the rest of the electromagnetic spectrum comes in the search to find home. So this was the loudest localization, and as Gabby mentioned, the non-detection with Virgo brought it down to 31 square degrees. In the 31 square degrees, there were 49 galaxies, because LIGO can also constrain the distance of the event to 40 plus minus 8 megaparsec. And then the question is, which of these galaxies is the true home of the merger?
A video wall was set up in the main exhibit hall for shorter oral presentations. This one shows transit data on the 7 planets discovered orbiting the dim red dwarf star TRAPPIST-1, in which 3 of the planets are believed to be in the star's habitable zone, where liquid water might exist on the surfaces.
add some sort of optical field for objects.
Another
when
presenter
can
touched on how
circumstance
raw
when it's
data is
available.
processed into the
Because
beautiful
it does
astronomical images we
overall
get
add
to
to
see.
the aesthetic appeal, but also the comprehension of it. So on the next screen, of course, when we're working on our data sets, we start all of it from essentially what's ones and zeros, right? Our information that we start with is pretty basic to begin with, and then we have to use software in order to translate that information. Now, one of the reasons that I wanted to show this slide is mostly that when we're working with non-expert audiences, the fact that these images are not giant space selfies is not actually all that known to a lot of non-expert audience members. So the fact that there are people working on creating these data visualizations, that there are obviously inherent biases in any person that's working on them that has a specific point that they're trying to get across, that's not something that people always recognize. So when they find that out, sometimes it can be not just a little bit of like surprise, but also distrust. So one of the other things that we do try to recommend when we're doing our data visualizations is to clearly explain how the images were created, and even put a face with the observation, with the visualization itself, so that people kind of get a sense of these are not giant space selfies.
As awareness of our impact on the environment grows, many AAS members are looking for ways to reduce the carbon footprint of these large meetings and of the transportation necessary to gather for them. Numerous suggestions for reducing the carbon footprint have already been made by participants on this notice board here, including going paperless, putting up more water bottle refilling stations, or making more of the posters in electronic form for remote access.
For fun, this AAS meeting hosted demonstrations on how to make your own comets. By mixing water, rock, and other chemicals together, you can make your own dirty snowball, as it's often called.
How about getting your own radio telescope for your backyard? You can get your picture taken at a special photo booth here at the AAS meeting. See yourself on the surface of Mars, or flying through space in the Orion capsule, or on the International Space Station.
Everyone tells me I have my head in the clouds. Guess they were right.
Virtual reality teaching tools are also on display here at the AAS meeting. The Space Telescope Science Institute is using this one to promote the upcoming James Webb Space Telescope. They're also using this tool to educate about the properties of our own planet, simulate a voyage in between the planets in our solar system, and to educate about the properties of protoplanetary disks. Educational exhibits include this inflatable planetarium by Digitalis Educational Solutions, here also on display at the AAS meeting.
So I'm Carrie Berglund with Digitalis Education Solutions. We make digital planetariums for portable domes and fixed domes. Behind me we have a 5-meter portable dome, and we've been taking American Astronomical Society attendees in and demonstrating our planetarium features. We can take people off Earth, even fly outside the Milky Way galaxy, rotate a model, and talk about the structure of our universe.
Well, this is the last day of the meeting. We've had thousands of attendees, presenting hundreds of posters and talks. Exciting news in the field of astronomy, ranging from latest updates on missions to search for exoplanets, new and faster ways to measure the masses of giant black holes, and turning what we thought we knew about the planet Jupiter completely on its head. All in all, the last 4 days have been a complete success. This is Robert Mitchell signing off from the 231st meeting of the American Astronomical Society.